Carnap so that I can show you what it's like to enter proofs in the Carnap proof environment. And I'm going to work through a couple of example proofs that use the rules that were covered in the previous videos. So a couple of things to keep in mind when doing proofs in Carnap. We use all the usual keyboard substitutes for logical symbols. But when writing a line of proof, you write a colon before the rule that justifies that line. So the colon says, I've written the sentence, now I'm going to give you the rule. And although there's no rule that justifies a premise of an argument, for Carnap, we write colon PR after each of the premises so that Carnap knows that it's a premise. And that allows Carnap to structure the proof appropriately. Finally, we won't write in want at the beginning of the proof. That was just a note to ourselves anyway. We still want to keep in mind what it is we're trying to prove because that's the sentence we're headed toward. When we get to the conclusion, we're done with the proof. Okay, here's an example. Problem A. Given H and G, we want to prove G and H. So we start with H and G and colon PR to indicate that it's a premise. Notice here on the right, here, Carnap is constructing the proof as it'd actually look as a proof. And here, we're typing out the sentences and the rules. So we have H and G, and we know we have the and elimination rule. If we have an and sentence on a line, we can write out either conjunct. So we can write H and elimination 1. And notice also, so if we write G, notice Carnap starts to write, I can't read this line. It's expecting a rule. So this little triangle with the exclamation point in it means there's something wrong with the line. It's not done yet. But again, G by and elimination on 1. And Carnap gives it a plus over here on the right-hand side of the proof when the line is complete, when it has a sentence, and when that sentence is justified by the line that we've written down. So keep in mind we want G and H. We've derived H on its own line, G on its own line. We can use and introduction on 3 and 2 to complete the proof. So Carnap realizes that we've gotten to the sentence that was our goal sentence, so it highlights the top in green and puts a check mark there. Okay, so let's look at another example. This example looks more complicated. It's got arrows in it, it's got knots in it, but if you look at the structure of it, it's saying if you assume M arrow J and not Q, you can prove not Q and M arrow J. And I've already got it set up so that we have this first premise. This first premise has an arrow in it, it has a knot in it, but the main logical operator here is the AND. So the only rule we have that we can use on that is AND elimination. And if we eliminate the AND, we get either M arrow J or we get not Q. So notice we're following exactly the same pattern as we did in the previous proof. We're taking a conjunction, an AND sentence, and splitting it into 2 parts using AND elimination. And we can put together the conjunction we want using AND introduction. So this is 3 and 2. And there it is. Carnap recognizes that we've got the complete proof, gives us a green and a check. And remember, if this were a homework problem, you'd still need to press submit to make sure Carnap recorded it and you got credit for it. The thing to note is that this proof has exactly the same structure as the previous proof we did. It's just that the sub-sentences, instead of just being sentence letters, are sub-sentences with arrows and knots. But structurally, we're doing the same thing. We're splitting apart an and we're putting it together an and in a different order. Okay, so let's look at another proof. So problem C gives us three premises. There's a biconditional, L and M, biconditional J and K. And this first premise, we can't really do anything with, because if you think about the biconditional elimination rule, it says if you have one side of the biconditional, you can derive the other. Or if we had J and K, we could get L and M. But we don't have either of those things to work with. Line 2, though, J biconditional K, we have J as another premise. And that means we can get K by biconditional elimination. We have the biconditional on line 2, and we have one side of the biconditional on 3. So we've got K. Now what? Well, we can do this. If we have things on two lines, we can put them together to make a conjunction. So we get J and K by biconditional introduction 3 and 4. Now the reason why I'm doing that strategically is because there's a J and K here. If I had J and K, I could use the biconditional on line 1. And when I do that, it gives me L and M. That's biconditional elimination. The biconditional is on line 1, and the 1/2 of the biconditional is on line 5. So we write down the other half. Now what? Well, I was actually just putting things together there. If we keep in mind where we're headed, we want M. The only place where we see an M in line 1. We see an M in line 6. We want M on its own, though. And we can get that from line 6. We can have M by conjunction elimination on 6. And that completes the proof. It shows that given these premises, we can prove M. Carnap marks it with a check. Again, a reminder, if this were a homework problem, you'd want to click Submit. Okay, one last example. Take a look at this problem. Here we have two premises. One of them is the conditional A or B, arrow, not C or D, and the conjunction B and not C. And what we want is D as a conclusion. And for this example, I'm going to think a bit more strategically. For the examples so far, I've just looked at the premises and worked on them and seen what I could derive. But here, I want D at the end. And notice, Carnap isn't happy with any of this. I'm going to have to fill in lines, justifications, that let me get D down here late in the proof. But where could I get D from? Well, take a look at this premise. It's got not C arrow D in it. So suppose I could get that. I can't get it out directly, but suppose I could get it. How would that let me get D? The conditional elimination rule requires two lines. Notice Carnap still has a question mark here. Error on line 8. Dependencies are of the wrong form. And then what that means is I don't have line numbers here yet. And until I have the right line numbers, line 8, what's currently line 8, isn't done. So if I were going to eliminate this conditional, what else would I need? How does the conditional elimination rule work? And the answer is conditional elimination requires two things. It requires the conditional, which I have, and it also requires the antecedent of the conditional. So I would need not C from somewhere. Okay, so how could I get those? Currently, I've got these floating in lines 6 and 7. How could I get not C arrow D? How could I get not C? Well, I could get not C from line 2 by conjunction elimination. So notice Carnap is now happy with that line. I've got a justification for it. Not C arrow D, well, I could get that from line 1 by conditional elimination. But remember that conditional elimination requires two things. It requires both the conditional and it also requires the antecedent of the conditional. So I'd have to have A or B. Okay, now how could I get that? This is all thinking strategically. It's how could I get to the conclusion I want? I could end up with D, and if I clean it up a little bit, I can do it this way, just to make it clearer what I'm doing. I could get D if I had these things that I have on line 6, I have now on lines 6 and 7. I could get this one. I can already get that one. Not C arrow D, I could get from this conditional if I had A or B. Where could I get A or B from? Well, a natural thought is, what could I do that would do disjunction introduction? Well, disjunction introduction, if you go back and you look at the sheet and you take a look at the form of the rule, requires that I either have A or I have B. So let's suppose I could get B. And now I recognize, oh, I can get B from line 2. In fact, conjunction elimination on line 2 gives me B. So I don't actually need this line. If I were working on paper and I'd already filled in these line numbers, I'd probably just fill in something to fill in this gap. But in Carnap, I can erase that line. Everything shifts up. And now I have to make sure my line numbers are right. On line 3, I got B by and elimination on 2. Yes. Now I get A or B by or introduction on 3. Then I get not C arrow not C arrow D, and that's conditional elimination on 1 and 4. Then I get not C by and elimination on 2. And then finally, I get D by arrow elimination on 5 and 6. So that's the complete proof. So I deliberately worked through this strategically. Proof strategy is something we'll get to more next week. We'll get to it more in further videos and further modules. If you couldn't have done this proof on your own, that's okay. At this point, what's important is that you can recognize the structure of a proof and that you can recognize how the rules apply. So if you didn't follow along with what I was thinking through, what my thought process was in constructing this proof, that's fine. What's more important is if you look at this proof over here on the right, now that it's completed and you look at each of the lines and you check the rule, can you recognize why the rule applies? That is, why is disjunction introduction legal on line 4 when it's applied to line 3? Why is that a legitimate application of the rule? That's the kind of thing you should be trying to learn now, because understanding how rules apply is a crucial step in eventually being able to do your own proofs.